Thank you. So I talk about dynamic adaptivity, and the way to obtain it will be based on wavelets. Some of the building blocks will be using wavelet constructions, and this is a joint work with Nicolas Kevlahan from McMaster University in Canada. So what I'd like to achieve is to present the work we've done, and also to present the more general ideas that we've implemented, but that could be implemented in a different way in a different situation. So we'll target the shallow water equations and some specific scheme, which is a C-grid hexagonal grid scheme with this kind of grid as a target. So this is a good choice from a certain point of view. It has good numerical dispersion, so that's due to staggering. So pressure will be in hexagons, and we have normal velocity components at the boundaries between hexagons, or they can be considered as tangential components along the triangular edges. It has some mimetic properties, it has some conservation properties, mass, vorticity, and either energy or entropy. So the basic scheme will be the one designed by Thuburn, Ringler, Skamrock, and Klemp, known as Théorique. And one reason to put mass on hexagons is that we still have a numerical mode due to the imbalance in the numbers of degrees of freedom between mass and velocity. So that's inherent to these staggered grid schemes, but it appears not to be too damaging if mass is on the hexagons compared to the case where mass would be in the triangles. So from this point of view, it's a good choice, but if you want to do adaptive mesh refinement, that looks like a terrible choice, because your mass control volumes are not nested at all when you perform a dyadic refinement of your grid. And the scheme uses the vector invariant form of the equations, and that will be somehow important in the way we do the mesh adaptation. Okay, and on the other hand, Nicolas had been using and designing dynamically adaptive wavelet-based methods for CFD for a number of years. So these wavelet-based methods, they are, I would say, established for CFD. So they have been working for 15 or 20 years. They are based on collocated finite differences, and that means they usually don't have any conservation properties built in. I won't use that, but they can solve elliptic problems on adaptive grids for incompressible Navier-Stokes equation, for instance. And typically they involve 2D or 3D Cartesian meshes, so that's an example of a 3D incompressible flow behind a spherical object, and that's the adaptive grid here. But you can also design these methods on icosahedral meshes, and Nicolas had worked on that a few years ago. So the work here is basically to extend these methods to these staggered grid conservative schemes. So before I go into the details of the method, I'd like to frame this in terms of building blocks. Okay, so basically I would construct some building blocks which work together to provide an adaptive method, dynamically adaptive method. And so these building blocks are a restriction operator from a fine grid to a coarse grid, an interpolation operator in the reverse direction, an operator to restrict fluxes, and kind of separately we'll need some refinement criterion to drive the dynamic adaptivity. And first, before going really to the hexagonal or staggered grid, I'd like to show that these building blocks are at least implicitly available in the classical AMR methods. So I'd like to start from this and explain how you can build analog building blocks in a more complicated situation like this one. So if we think in terms of AMR, AMR works very well in the case where we have hierarchically nested finite volumes, like in this, so that's taken from a paper by Christian Jablonovsky. That's from the Icon website, and that's two-dimensional, but if we think in one dimension, so my hierarchy of nested finite volumes is quite obvious, so that's my coarse grid and finer grid and finest grid, and this cell can be split into two cells, and each of these cells can be split into two cells. Okay, so we have a hierarchy. And a function can have a high resolution representation on the finest grid, or slightly less accurate representation here, or a very coarse representation here. So that's quite obvious. And now typically if I do an AMR on this kind of hierarchies, I will describe my grid as a collection of cells of different sizes. So I'd prefer to take a different look at this situation and say that actually I'm using these nested grids, but at each level I'm using only part of the grid. So this cell belongs to that coarse grid, and that cell here belong to that finer grid, and these two cells here belong to that finest grid. Okay, so that's I'm not introducing, it's just rephrasing the same thing differently. And now I can talk about operations that bring information between the different resolution levels. So there's an obvious restriction operator from fine grid to a coarse grid, which is simply to sum up the contents of these two cells, and that gives me the contents of that one cell. Okay, that's exact actually for a finite volume method, or GG. And now I can do the reverse, and to interpolate from coarse to fine. If I have a finite volume method, usually I'm able to do, say, a linear reconstruction inside each cell. And I could use this linear reconstruction to compute the integral inside a subcell. Okay, so if I'm able to do a linear reconstruction, which any finite volume scheme is usually able to do, then I have a built-in interpolation operator in my method. And finally, I can also restrict fluxes. So if I need the flux between these two cells, but this cell is actually split, I will typically compute the flux on the finest grid and transfer it to whatever coarser grid I need to. So that's in 1D, I will just copy the flux, and in 2D, I will accumulate the flux on this interface between the coarse cell and two fine cells. Okay, and the reason why this makes sense is that there is a kind of trivial commutation property hidden here, which is that this restriction is consistent with the way I can restrict mass. So that's quite trivial, right? So if I compute the divergence on each of these four cells, and I sum up all the divergences, then all the inner fluxes will cancel, and I end up with just the outer fluxes. So that means if I have a flux on that my fine cell grid, I compute my divergence, and I restrict this divergence to the coarse grid. I obtain the same result as if I restrict my flux. So here, just summing up these two fluxes, these two ones here, the two here, and the two here, and taking the divergence on the coarse cell. Okay, so this is all implicit in AMR methods, and together I can bring them together and solve my do all the required calculations on my multi-resolution grid. Right? So for instance, if I need this flux, so typically I will need my Riemann solver will need the left and right state. So I need that yellow state here, and this and also I will need a reconstruction here, so I will need this yellow box too, but both of these can be obtained by interpolation from the coarse grid. So I would first interpolate here, compute my fluxes, and bring my flux to the coarse grid, and I can compute everything I need to advance my degrees of freedom in time. Okay, so that works very naturally in the AMR method, and that's really based on these three building blocks. Okay, and one thing here is one special thing here is that I've used this interpolation operator to actually hide from the finite volume scheme the fact that we are working on a refined grid. So I'm handling the fine coarse boundary kind of automatically by using this interpolation operation. Okay, so the finite volume scheme doesn't have to know how to handle fine coarse boundaries in this setup. This is handled by the interpolation operator. Okay, so I can handle fine coarse boundaries, so I can hide the multiscale nature of the grid from my underlying scheme. And I would like to do this in the more complicated situation I've outlined at the beginning. So I want non-nested grid hierarchies, I want staggered grids, and I may want additional conservation properties, especially vorticity. So one question we may ask here is, where are the wavelets? There is no wavelet here at all. So the wavelets, they will be involved for three purposes. One will be to remove redundancy in their multiscale representation. So here, for instance, these 2 degrees of freedom are sum up to that green quantity here. So the green here and the 2 blue here, they are related by some constraint. And in this case, it's very easy to deal with this redundancy, but in the more complex situation, the wavelets will help us deal with more complicated redundancies. They will help us construct these interpolation and restriction operators in this kind of setting. And they will provide error estimators to drive the refinement. So that's what we will see in the end. Okay, so that's the outline of the remaining part of my talk. So first I describe how we can construct restriction and interpolation for a velocity field which is on a staggered mesh. And I introduce the discrete wavelet transform at this point, and also the filtering and error control and compression that can be achieved based on this. And if I have time, I'll explain how I can construct the restriction and interpolation operators for mass and pressure and mass flux. And if I don't have time, I just show the result. And spend some time on discussing how this can all be combined together to yield dynamic grid refinement, and especially the refinement criterion based on some error analysis. So let's start with velocity. So my degrees of freedom, I will interpret them as the velocity integrated along the edges of the triangles. So this is a coarse triangle, which is, well, actually this is a coarse triangle, and this triangle can be diagonally subdivided into 4 triangles. And then there is a trivial restriction, which is like in the AMR case. So to compute this circulation here, this integral, I would just add this one and this one. Okay, and do the same on all edges. That's my restriction. Okay, so velocity is easy because I'm essentially, when the mass is on the hexagons, dealing with velocity is easy, and when the mass is on triangles, dealing with mass is easy. So what properties does this restriction have? if I compute the curl on my coarse grid, then it is the sum of the curls computed on my fine grid. Okay, so I have a consistent vorticity field across scales in that case. And that's because here I'm in a situation which is similar to the AMR case for mass. And another thing, later on I will, in my equation, one of the terms is a gradient. It's the gradient of the Bernoulli function. And I will take a gradient, say, from between this point, and another gradient between this point and that point. And it will be a simple finite difference. And you can see that if I take the gradients between these 2 points, right, it's just the sum of the gradients between here and there and here and there. Okay, so what I have is this commutation diagram. So before, in the AMR, what I had is I could have the commutation for the divergence operator. I was able to restrict the flux from the fine grid to the coarse grid, and I had a consistent divergence. And now I have a consistent curl, so that's what I explained first. So if I take the curl on the fine grid and restrict, it's the same thing as restricting velocity and taking the curl. And I also have the same thing for grad. So I can take the grad on the fine grid, do my restriction, and it's the same thing as taking the grad directly on the coarse grid. So that will guarantee that I don't generate vorticity when on my adapted grid. I mean, the gradient term doesn't generate vorticity on the adapted grid. Okay, so now I need an interpolation formula. So to go from this coarse grid to this fine grid. So I will need additional information from my neighbors if I want a better than first order interpolation, and that's, well, you can do it several ways, but that's the way we did it. So we consider this triangle and we add this neighboring information. So that's similar to piecewise reconstruction in a finite volume scheme. You will use the left and right neighbors to compute the slope. And you can just do the linear algebra and find the weights that give you the velocity on these blue arrows here and on these red arrows here. And the property of the interpolation formula we can build is it's consistent with the restriction. So that means that after I have interpolated, the sum of these two red arrows is exactly my blue arrow here. And it's second order accurate on the regular hexagonal grid on the plane. And we can do something similar on the sphere. Although I will not show any results on the sphere, that's ongoing work. But for instance here, if this point is a pentagonal point, that this still works. Okay, so we don't have to take special care of pentagons here. Okay, so I have a restriction which is quite simple. I have an interpolation formula which looks like a linear reconstruction in a finite volume scheme. And now I can start doing wavelet stuff. So I will describe the discrete wavelet transform. So the idea is to provide another description of the same data. So I have these velocities on my fine grid, and I can perform one restriction, and of course I'm losing some information while doing this, and I can do an interpolation back onto my fine grid. And if I compare the two, I will find the high resolution details that were contained in my data here. So comparing just means that I will take the difference between the interpolation value here, the interpolated value here, and the original value here. And because my interpolation is consistent with my restriction, the sum of these two is equal to this one, and it's equal to the sum of these two. So the differences between this and that, and this and that, are sum up to 0. Okay, so actually so that's my wavelet coefficient here, which is the difference between this and that. The two wavelet coefficients here are equal and opposite. So I need only one of them. They contain the same information. So what I've done, I have replaced this information on the fine grid with information on the coarse grid plus wavelet coefficients. And I have exactly the same number of degrees of freedom. So what to do, and I can repeat this process as many times as I need. Of course, I will have several levels of refinement. Okay, so now I can, so that gives me a way to remove redundancy. What I have done, I have replaced a fine scale representation of my information by a coarse scale plus details. So I'm able to handle separately the coarse scale and the fine scale details. Okay, so I have an error estimator by construction. This wavelet coefficient is an estimate of the error that my interpolation procedure is doing. So I will be able to use this property to do some filtering or compression, and typically I will tend to drop all wavelet coefficients that are lower than a certain threshold, and by this way I will introduce errors that are less than this threshold times some constant. Okay, so this can actually be checked numerically. So one thing, this transform is invertible. Okay, so I can also come back from that representation of the data to this one. That's very important, because in practice all the numerical scheme will work on this information. And it's actually quite trivial. You take your coarse value, you interpolate to the fine grid, and you add the wavelet coefficients. So now if I take some test field, some analytic test field, I compute it on the finest grid, I compute all my wavelet coefficients, and I remove everything which is below a certain threshold, and do my inverse transform back onto the finest grid. I can compare my full complete data and my filtered data and verify that the error that I'm introducing is proportional to the threshold I have decided. Okay, so these are L1, L2, and L infinity norms. So I have a local error control in L infinity norm. And this is compression, so this tells me how many wavelet coefficients I need to represent my signal to a given accuracy, and how fast this n decreases depends on the accuracy and the interpolation, and on the smoothness of the data, of course. So here we are in 2 dimensions, and we have a second order accurate interpolation, so the number of degrees of freedom is inversely proportional to the error, to the accuracy. Okay, so that's it for velocity.
Question on that.
Yeah, I can take questions anytime.
Does that play the role of a refinement criterion? Just
yeah, so they will be used in the refinement criterion.
So the criterion for compression is, in a sense, a refinement criterion, but it doesn't look like the usual refinement criterions that we've seen.
Yeah, so in a sense, so what this wavelet coefficient is doing, it looks like a local second derivative, because it's the error that you're doing in a linear interpolation, so it's kind of proportional to your second derivative of your function. So it's not, so usually you would take a gradient-based heuristic refinement criterion. So that's not exactly the same. You can draw some analogies with other criteria. But I come back to in detail to the refinement criteria later. Okay, so now I think I have time to explain how to deal with pressure. So pressure is the harder part. So I'll start with doing something which doesn't do all the job, but it does part of the job. And the hard part is the restriction. So I'll skip this for the moment. I'll do something very simple for the restriction. I just take these fine values and copy them onto the coarse grid. Okay. That's not very accurate, and it lacks many properties you want, but let's do this for the moment. And then I will use a simply centered linear interpolation. So I can interpolate from these 2 points to this point here, and I can compare this one and this one again and define my wavelet coefficient. Okay, so here it's really a second derivative that we're building, right? The weights will be 1/2, minus 1/2, minus 1/2, and plus 1 here. So that's a kind of Laplacian. Okay, so if I just do this, I already have the error control and compression properties I had for velocity, because this really depends only on the interpolation step. So I can take my fine scale signal, represented on the coarse grid as these values plus wavelet coefficient, and do the filtering again. And I can control the error I'm doing. So from this point of view, that's good enough. That's enough for refinement. But that's not enough if we want to conserve mass. So if we want to conserve mass, we need this commutation diagram, which we had essentially for free in AMR. So I would like that when I compute some divergence and I restrict to the coarse grid, this should be the divergence of something. So if it's the divergence of something, it has a zero average. And the only way to make sure that this has a zero average is if this mass restriction operator conserves the average of what you're taking on the fine grid, which is obviously not the case here, since I'm just dropping all that information here. So to have a mass budget consistent across scales, I need that my restricted mass field has the same integral as the fine scale. So you need to have the same mass, whatever the scale you're looking at. All right, that makes sense. So the solution comes from, there is a solution in the standard construction of wavelets called a lifting step. And it works like this. So what I've done here on hexagons, I can do it in 1D. So my coarse points will be these ones, so the even indices here. And for the moment, I've just taken that value from the fine grid and pretended it's the same value on the coarse grid. So when I'm doing this, in terms of the average, I am replacing the area below that black curve by the area below that other curve, right? Because I'm doing a linear interpolation. So my restriction operator implicitly replaces this curve by that curve. So I'm I'm missing this gray shaded area. And it turns out that this area is exactly 1/2 my wavelet coefficient. Okay, because the wavelet coefficient is the difference between this red point and this gray point here. So one way to recover my real correct average on the coarse grid is to take 1/4 of this wavelet coefficient and add it here, and that will lift a bit this point, and the other 1/4 here, and that will lift a bit that point. And now that curve here covers the same area as my original black curve here. Okay. So the property of that, so the main advantage of this way of doing is that you can still invert the transform. You have an explicit local invert. Okay, so in more formal terms, if I'm on a hexagonal grid, so what I've done for the moment is I have some interpolation formula which takes some linear combination of my blue points. So these are the coarse hexagons. So actually I'm just using a centered average between these 2 points. And that defines my wavelet coefficient. And now the lifting step is here. I will take this detail coefficient and I will add a fraction of it to each of its neighbors. And you do the algebra and find what this coefficient must be to conserve the total mass. And to invert this transform, I just shift this on the left hand side and that on the left hand side, and I got an explicit inverse, which is just I first subtract my linear combination of wavelet coefficients to get the fine scale values at coarse hexagons, and then I use my interpolation formula plus detail to obtain the fine values at new hexagons. Okay. So if I, in more concretely, so that's the stencil for my wavelet coefficient. So I'm subtracting the average from the values on this fine hexagon here. And I will add 1/8 of this to my coarse hexagon here. Okay, so if I combine the two, this is the total stencil I get, and you can show that this conserves total mass, and you still have the invertibility I talked about. Okay, so now we preserve mass, so we can hope for to find a consistent mass flux restriction. And I think I'll skip a little bit. No, I don't have to skip anything. I just give the result. It looks like this. Okay, there's nothing magical. There's some details in the paper. But basically, now we also achieve the same thing as we had on AMR, despite the fact that the small hexagons overlap with the large hexagons. Okay. So now we have all the basic ingredients to do dynamic grid refinement. So the grid refinement I talk about will be focusing on the degrees of freedom as opposed to the grid itself. And the reason is that the grid itself doesn't lead it naturally to grid refinement. So it's more, actually the only way to think correctly here is to think in terms of degrees of freedom. So I explained that first, how it works in the finite volume AMR context. And then I will do some error analysis to devise a refinement criteria. So what do I mean by degree of freedom based adaptivity? So essentially I try to express the refinement and de-refinement procedures in terms of the degrees of freedom I'm prognosing, rather than in terms of grid cells. So So in AMR, I can replace this operation of splitting a cell by an equivalent operation on degrees of freedom, which is replacing one coarse degree of freedom by a number of fine degrees of freedom which are contained in the cell. And conversely, when I merge cells. So now I can think of refining and derefining in terms of adding or removing degrees of freedom. And since I have my wavelet coefficients give me a set of degrees of freedom, refinement or derefinement will be obtained by expanding or reducing the set of prognosed wavelet coefficients. So in a 1D situation, that will look like something like this. So I apologize, here it's the fine scale and here it's the coarse scale. That's opposite to what I've shown before. So here I have a region which is highly resolved and very localized, but otherwise I have a quite coarse resolution elsewhere. So the dark dots are the wavelet coefficients which are above a threshold that I will determine later. And because this may move in space, left or right, and because I may have nonlinearities which will generate small scales, I also add these adjacent coefficients. So I will prognose them although they are below the threshold, because they might become, as time passes, larger than the threshold. Okay, so this goes like this. So that's, I think that's a Berger's equation in 1G with some explicit diffusion. And by this strategy, I can track the front. So the adjacent wavelet coefficients on the left and right will enable to track the front. And here I don't have the movie, but you can also start from a smooth solution with a steepening front and see that the wavelet coefficients become activated at finer scales progressively. Okay, so that's what we are going to do with the wavelet coefficients, and we can think of AMR the same way, although it's a bit unnecessary. So in AMR, the degrees of freedom are the blue ones here. So for a wavelet, a complete calculation of the tendencies in the wavelet context. So my purpose is to compute the time evolution of each wavelet coefficient. So for this, I will actually compute the time evolution of all the values that are involved in that wavelet coefficient in the stencil. So for instance, in this case, if I want to compute the wavelet coefficient associated to that cell, I'll need to compute the evolution of the two blue boxes here. So for this, I will use my numerical scheme, whatever it contains. And here this will be essentially a divergence operation. Okay, so and to this divergence will be applied to fluxes, and these fluxes will be computed from the state inside each box, and the state inside each box will be obtained from the wavelet coefficients. Okay, and here each of these arrows is partial. I mean, I'm not doing this on the entire grid. I'm doing this only where it's absolutely necessary. So in the AMR, I would, for instance, to compute this divergence, here I will need these two fluxes, and to compute this divergence here I will need these two fluxes. So I need to compute these three fluxes, and to apply my Riemann solver here, I would need actually these two ghost cells, for instance. And then my interpolation, I will make sure that these ghost cells are present here. So that would be actually at the finest level, and at the intermediate level, I also need this flux to have the content inside that cell, but the flux here can be obtained by restriction from the lower level. And at the coarsest level, I will need that flux, and this will be obtained by restriction, and this other one will be obtained by a calculation on the coarse grid. So there is a certain amount of bookkeeping going on, but you can actually determine at each step where you need to do the calculation, where you can restrict from the final grid, and where you need to do the calculation on the coarse grid. Okay, so that's basically the algorithm. I think I come back to here if you have questions. So now I'm able to do the calculation. Okay, I hope it's more or less clear how I can get these tendencies given these coefficients. And now I need to make one last decision, which is which coefficients to keep and which one to drop. So for this, I'll do some error analysis. And the basic underlying ideas is that if I drop a wavelet coefficient, then I will make a small error on velocity and pressure. And this error will propagate to the trends through the numerics. This will add to errors which are already present, which are the truncation errors of my numerical scheme. And we want to keep all these errors smaller than some predefined value. Okay, so this will have two consequences. So I first make a kind of rough analysis on the simplest possible equation, which is just transport. So dp dt plus u grad p equals 0. So first I want to make sure that the discretization error that accumulates during one time step remains smaller than my threshold, because otherwise I will refine my grid only to resolve numerical errors, and I will have runaway refinement. Okay, so I can estimate the error I'm doing on my gradient, so that will depend on a certain derivative of the solution and the local mesh size. And the n here depends on the accuracy of my numerical scheme. And I can make a rough estimate of this if I have a typical pressure fluctuation and I have a local characteristic size of the solution. So this depends on the solution, and this depends on how much you have refined. So I decide to throw out every wavelet coefficient which is below this threshold. So delta p is my typical fluctuation, and epsilon is a relative tolerance, 0.1 or I don't know, 10 to the minus 5 if you want to be very, very accurate. Now the filtering error goes like this, and this depends on the accuracy of my interpolation formula for the wavelets. So that's my local error indicator. And so if I have a given threshold, if I have decided on this threshold, I will refine until h is sufficiently small that this is on the order of that. Okay, so by choosing this epsilon, I'm actually deciding h here. So if I compare this and that, I'll find that for the truncation error times delta t to be less than the filtering threshold, I need a Courant number smaller than this. And typically epsilon will be less than 1. So if if m is larger than n plus 1, I have a problem, because this will restrict my time step, and I don't want this to happen. And what this tells us is that m should not be too large, so I should not take a fourth order interpolation if my numerical scheme is only second order accurate. Because then my error indicator will not be a good estimate of the local truncation error of my scheme. So that's actually quite moral. The wavelet interpolation must not be more accurate than your scheme. So you will not gain anything, and you actually can get runaway refinement unless you take a penalty on the Courant number. So now we'll take, so here n is 2 because that's the scheme we've chosen, and all our interpolations are second order accurate, and we are safe. So now I can look at the error on the trends. So I take my equations and I look at how errors in U and P affect the trends, and I do some algebra. I can give some details if I have questions, and I get this kind of estimate. So that's if I want to capture a gravity wave, for instance, which has a typical flow velocity of U, with c being the gravity wave speed. So if I want a relative accuracy of epsilon on the trends, I need to fix these thresholds on my wavelet coefficients. Okay, and so this shows that we actually do control the error on the tendency now. Okay, so I filter U and P according to these thresholds, and I check that the error that is propagating to the tendency is scaled linearly with epsilon. So now I can do that. Okay, so with this I can run my adaptive simulation, and it seems to work. So on the left is the solution, on the right is just a map of the active pressure points, and the color coding is how the depth of the refinement. So we are very refined in the center, and the criterion is able to refine where the wave is arriving and to de-refine where the wave is leaving. And you can, so that was for a small amplitude wave. You can do that with a larger amplitude, in which case you get a strong steepening of the wave, and the mesh is able to follow this. I show this again for another test case. And if now I'm looking at a harder situation where I'm in near geostrophic balance, then I need to be more strict on my thresholds. And the reason, I can go back to the reason for this. Whoops. Okay. So if I'm close to geostrophic balance, then the characteristic time scale here will be a slow scale. And so it will not be c squared u over L, it will be c u squared over L squared. So the characteristic time scale will be u over L instead of being c over L. So since it's overall slower, to get the same relative error on trends, I need a smaller absolute error on trends. So I need a lower threshold on velocity and pressure to achieve the same relative error on trends. So I get this kind of scaling, and you see that for a given velocity, for a smaller Rossby number, you will need to make very small errors on u in order to correctly balance the pressure gradient and the velocity. And we can still control the error and tendency as a function of the epsilon, and do this kind of simulation. So that's between turbulence, and here the degrees of freedom will track the development of vorticity and vorticity filaments. So there is an intermediate phase of turbulence, and after some time it settles down just a pair of counter vortices. then you can, so what I shown was for a relatively low tolerance. So that means you need a relatively large number of degrees of freedom to achieve this tolerance. But you can, so that was 0.15, and that's what you get for twice as large a tolerance. So obviously it's a bit more noisy, but you still capture the qualitative dynamics in that case. And of course you refine less. And a word about compression. So the point of all this is to have fewer degrees of freedom to prognose. And this can be measured here and measured by a compression factor compared to a uniform resolution grid. So we wanted really to have this turbulent test case to have an estimate of how much we can compress in this case, and not in a case where we have just an isolated or coherent structure. So in that case, we still get a compression ratio of a few tenths, depending on how we compute. And that's the computation time per degree of freedom, which is constant. So the cost is linear in the number of degrees of freedom. The numerical scheme here is entirely conservative. There is no explicit dissipation, and it's a centered scheme. But due to the dynamic adaptivity, there is some removal of energy as time goes by. And as you lower the tolerance, so this will be for a high tolerance, and this will be for a low tolerance, so a better result simulation, there is a slight decrease in the energy dissipation. Okay, so these are the spectra. So we can measure the energy dissipation, and at the same time we can measure a turbulence scale and devise an equivalent viscosity or turbulent viscosity and a Reynolds number. So what this shows here is that as you decrease the tolerance, which should be this here is this one, and this here is that curve, the effective Reynolds number is increasing. So if you put more degrees of freedom, you achieve a more turbulent simulation. Okay, so I'd like to summarize. So the building blocks I've been using, there are a restriction, an interpolation, and flux restriction operators. They provide consistent multiscale budgets. That's trivial to achieve in AMR. They manage coarse-fine boundaries. There are many other ways to manage coarse-fine boundaries, but that's one way. They provide local error estimates. And they provide a non-redundant multiscale representation. So that can be useful in non-trivial situations like the hexagonal grid. Okay, so that's if you're able to construct them, and the Wavelet tools can help you construct these operators in non-trivial situations. So I think the main idea that we've developed here is that this consistency conditions that achieve something analog to the accumulation of fluxes on coarse-fine interfaces in the AMR context. But we have vorticity in addition to mass. And then adaptivity on this kind of meshes is probably it's probably better to think in terms of degrees of freedom, because the grid is not very helpful. So we can cope with situations where grid-based adaptivity doesn't work. We can still preserve some discrete conservation properties like mass, vorticity, and it's still linearly expensive. And we've developed error-based grid refinement, so we try to we control the error in the computed tendencies. So this allows us to drop. So we do this by dropping features which have a low energy, whether they are large scale or small scale. Or another way to say the same thing is that we will resolve small scale features provided they have some energy. We still have induced numerical dissipation, which depends on the tolerance, and we have significant compression even in this turbulent situation. And we're still working on this to really do the spherical case, to introduce solid boundaries. We'd like to do some idealized ocean simulations, and then go to more 3D atmospheric equations. And on this implementation side, everything I've shown is done in MATLAB. So it looks complicated, but it's actually doable in MATLAB. And you can get linear cost in MATLAB with a large constant. So Nicolas has a PhD student who is developing a parallel tree-based, actually has developed a parallel tree-based implementation. And we can think of mixing the more NMR style and degrees of freedom based adaptivity to have some additional efficiency gains. I don't know if that's really critical. Thank you for your attention. I hope.
So this reminds me somewhat of the work that Ami Harton was doing on multi-resolution methods back in the late 80s.
In Harton,
or so.
yes. Harton,
yeah.
yes.
So he was only, I think, looking at 1D and looking at shock capturing methods, but it was a similar sort of idea of using these wavelet
yes.
basis
So actually,
expansions.
I've studied them at the very beginning. There are people. There is some literature from 90s, or just let me find this stuff. Yes. No, maybe I removed that slide. Okay, so there is some literature on combining finite volume methods with this wavelet error control, essentially. So in that situation, the additional value of wavelets is essentially to have a good theoretically understood error control, I think. While in terms of ensuring conservation and refinement, it's pretty obvious how to do it based on the grid. And so there is work by Harton, and there have been further work by Cohen in Paris and others later, and also Kai Schneider in Marseille.
But those weren't on staggered grids. Those were just.
Oh, I'm not aware
things, I think,
of one on staggered grids. So did Harton look at staggered?
No, I don't think
Oh, okay.
so.
You said you needed to extend this to the sphere.
Yes.
So the results you showed us were, I would guess, on a perfect hexagons.
Yes.
Has the extension already been made to non-perfect hexagons?
So on paper, yes. on paper, we can do everything. We can get all other properties the same on the sphere, except that we'll have a loss of accuracy. So some of the parts will downgrade from second order to first order accuracy. So it's not clear at this point if that will be critical or not.
The solver will.
The solver and also some parts of the interpolation or restriction will not be a second order accurate.
So you mentioned the local error estimate. So what kind of errors are you estimating? It's
So I'm estimating the It's the different. It's the error I will make if I de-refine.
So the relatively, it's not a comparison to the true solution.
No, because okay. So in the graphs I show, I compare to an analytic solution or to a reference solution. But in practice, when you run the model, of course, you don't have any reference. So it's you're just comparing the model at fine resolution to the same thing at a coarser resolution. Somehow that's what it's doing. So basically, the idea is that the wavelet coefficient will tell you the error you're doing if you de-refine, and it's supposed to be a good enough estimate of the improvement you can expect if you refine.
So it's an estimate. It's not the actual calculation of the error. Since
No, it's an estimate. So there is a
Estimate.
constant, a known
So
constant.
related to that, so this error, you're looking at the error in the wavelet representation.
Okay, so the amplitude of the wavelet coefficient is precisely the difference between the interpolated value and the actual value. I mean, not the actual value of the okay. Let me come back.
I understand that.
Yeah.
I think maybe what I'm thinking is you have this hierarchy of meshes, in essence,
Mhm.
refinements. You could think about, in some of the classical AMR going back to the 80s, people have used Richardson extrapolation or something that directly uses the solver to compute solutions at a different resolution, and then you can directly
It's a similar idea, I think.
get to the error.
And what I think, I'm not very familiar, well, I don't know the details of Richardson extrapolation, but I think what we're doing here is something like an analytical Richardson extrapolation by using some a priori knowledge of the equations and some orders of magnitude. So this could probably be replaced by Richardson extrapolation to handle more complex coupled cases or situations where you don't know in which regime you're working or what the characteristic scales are.
Any final questions? So let's thank Thomas again.